All right. Hello, everyone. My name is Bernd, and today was day 10 of Advent of Code. And today was a really interesting puzzle. I really enjoyed it. I hope you also enjoyed it. And yeah, it definitely took me some more time than usual to solve, and it also required quite a bit of code. But let's have a look into it. So we give them a loop today, something like encoded like this. So we got some straight parts and some bends encoded at F and S7 and J and L encode bends. And then one of the location is given as S, a starting location, and that's where some animal is hiding, and we believe it will go along the loop. And what we want to figure out is the furthest position from the start, how many steps this is away from the start. So furthest position not in terms of real distance, but in terms of steps within the loop. And yes, for that first we have to figure out the particular pipe at the starting position. So we told it kind of closes the loop, but we have to figure that out first. And also what makes the problem a bit harder is that there are additional pipes around which make it harder to see where the loop is and also will make it harder to parse the input. And yeah, so how can we do that in code? So of course we need to read the input, and then we want to have some kind of grid. So we want to have some notion of a position, and particularly we have an x and a y coordinate, and then I want to be able to do things like adding two positions, subtracting one position from another, and we also want to evaluate if two positions are equal by checking whether their coordinates are equal, and we want to be able to hash a position in order to be able to use it as a key in a dictionary in the kind of standard way we expect. Then with that, we can define some directions. So we want to, from a particular position, we want to consider the left, the right, up and down. And all of this will also have the corresponding position if we essentially take one step in a particular direction. And then we can define pipes. So we initialize a pipe given with a given position and the direction. And then the position and the direction will save, and then the next positions we will be given by essentially taking the position of the pipe and adding the position corresponding to the direction, to both of the directions, and the value will give us this part of the enum, so the position vector. And what we also want to, or what will be helpful, is having this next position, which takes a previous position as an input and then evaluates the next position based on that. So essentially we check if the previous position is one of the next positions, then we return the other one. And that's it. Yes, so then our grid will be a dictionary which maps each position either to a pipe or to none if there's no pipe at a particular position. And what we also want to know, as in the previous puzzle, is the valid neighbors of a particular position in the grid. For that, we just go through all the four directions and add the value of this direction to the position. But we only do that if the new position is in the keys of the grid. Okay, so that's kind of set up for the solve a problem. But what we also need is to parse the input, or what we need is to parse the input. So for that, we define this dictionary, which essentially maps all the pipe entries to particular directions. So this pipe will continue in the upward direction and the downward direction. So that we map it to a set of up and direction down. This pipe will continue in the left direction and the right direction. Then this L encoding stands for a pipe that continues in the up direction and in the right direction, and so on. So that will be useful to parse the lines. So with that dictionary defined, we can just start with this pipe at position dictionary empty, and then go through all the lines, enumerate to get the y coordinate, go through each single line, enumerate to get the x coordinate, and the character. If the character is a dot, there is no pipe at the position, so we set pipe to none. If the character is an S, there will be a pipe at the current position, but we don't know which one yet, so we also set pipe to none, but remember the starting position. And otherwise, we get the pipe directions by this dictionary, yes, and then we define a current pipe at the current position with the tuple of directions, and our output then will just be the dictionary that maps each position to either pipe or none. Okay, so the first thing we need to do to solve the puzzle is to place the correct pipe at the starting position. So we have two directions which this pipe will continue, and in both of these directions we need to have a neighbor which also points into the opposite direction, which points back, essentially back to the starting pipe. So we go through all valid neighbors of the starting position, and then consider the pipe at that position. If the pipe is none, if there's no pipe, we continue, that's not interesting. Otherwise, we check whether the starting position is in the next positions of the neighbor. If this is the case, good, then this is a correct neighbor of the pipe at the starting position. So then the pipe direction will go from the starting position to the neighbor position. So that will be the direction. And yeah, we saved that in our set of directions. And then we told that there should be exactly two. We double check if that's the case. And then we define this new pipe based on the starting position and then two direction we found and add that to a dictionary. And with that, we can solve the problem. So we parse our lines into starting positions and to find the starting position and this dictionary. Then we place the correct pipe at the starting position. And then we want to go around the loop in both directions. So the current position, we have two current positions at each time, and at the beginning they will correspond to the next positions from the starting pipe. We also need the previous position to know in which direction we're going. So for both current positions, that will be the starting position. And then because we already start one step away from the starting pipe, our solution will start at 1. And then we go around as long as the two current positions are not equal. And in each step, we just update the position for both the current position 1 and the current position 2. And for each step, we also increment the solution, and then that will give us the solution in the end. And in order to update the two positions, our last missing function, if we have a previous position, a current position, and a data dictionary, we just have the current pipe, and then the next position will be given by the directions of the current pipe, and we also supply the previous position in order to get the next positions. And then, yeah, this will return the current and the next position, which will set our previous position and our current position for the next step. Okay, so that's it for part 1. We should also run it on the test input, on both our test inputs. That looks good. So we can also run it on the real input, and it turns out it gives us the right solution. For part 2, it turns out we not only want to consider the pipe, but also the whole area enclosed by the pipe. So this might be a bit complicated. For example, in this example, these two positions would be inside the pipe, enclosed by the pipe. However, all of these are not, because in this example, you can essentially from the outside enter these positions, so they're not enclosed. And even if the width of this entrance is 0, they still don't count as inside. So it's only these 4 positions which would be inside in this problem. And so in order to solve this, what we can do is we kind of consider going along the pipe in, say, clockwise direction, and then going to the right from the pipe will always point us inside. So if you kind of imagine going along the pipe, and then to the right will always be inside. And then if you go here, and at this point, going to the right will give us this position. So it actually gives us an inside position. And if you go further along and are here, for example, in this part, then these positions will actually be to the left of the pipe. So they will not be inward position. So that's kind of a trick we can use to distinguish this inside area and the outside area. And our solution to the problem will just be the number of inside positions. All right, so how to encode this idea in code or in Python? So we can reuse almost everything from part 1. And then our solution will look the following. So first we have a list of lines, and then we parse it to get the starting position and our data. Then we place the correct pipe, as in part 1, we place the correct pipe at the starting position. And then what we want to get is the loop positions. And then what we'll do is we count the number of right turns based on those loop positions. And then we also find the number of left turns. And then we compare whether the number of right turns or the number of left turns is larger. If the number of right turns is larger, then that means this list of positions goes around the loop clockwise. So then we know this tells us how to turn inside. So this inside turn will be a dictionary that always tells us if we go along the loop how to turn inwards. And this turns out to be a right turn if the loop is clockwise, otherwise it's always a left turn. And then from that, we can essentially find the positions one step inside. So inside the loop, if we only do one step inside, those will be the positions that we can get to. And then from that, we can find all the other positions inside and count them. Okay, so of course we need to implement all the functions used in here. So first, a function that gets all the loop position is kind of similar to what we've done in part 1. So we have a starting position and a dictionary that gives us the pipe at each position. And then the current position will be just one of the next positions from the starting position. So we have the starting position, consider the pipe there and the next positions, and just take one of them for the first current position. Then that means the previous position at this part will be the starting position. And for the loop of positions, we start with a list of just the starting position. And then we go along the loop until the current position is equal to the starting position again. And in each step, we append the current position to the loop, to this list of loop positions. And then, just like in part 1, we update both previous and current position. Okay, then in order to evaluate this kind of right turn and find the number of right turns within a loop, we'll use this dictionary that tells us for a particular direction, if you turn right, what will be the new direction. So essentially, if you turn right, going up changes to going right, then turning something right by 90 degrees makes right direction turn into the downwards direction, down into left, and left into up. And essentially, a left turn will be all the opposite directions. So essentially mapping right to up, and up to left, and left to down, and down to right. Okay, we can use that to define this function that, based on 3 positions, tells us whether this is a right turn or not. So essentially, we consider the direction inwards, which will be the direction from the previous position to the current position, and the direction out will be the direction from the current position to the next position. Then we just check if the direction out is equal to a right turn on direction in, or the direction in turned right. Okay, we can use that to count the number of right turns inside the loop by just going through each loop, for each index in the length of the loop, or each index of a loop position, consider the previous, current, and next position based on this index, and then evaluate if the 3 positions make up a right turn together. Okay, so the next function need for a solution is this function that gets us all the positions that are one step inside. So for that, we again have the list of loop position and as an input, and also this inside turn, which is a dictionary to tell us for a particular direction when we go along the loop, how do we turn inside. And this function will return us all the positions one step inside, and also some that are part of the loop itself, but that's not a problem, we'll deal with that later. Okay, so we start with an empty list, and then again we go through all the indices and always consider the previous position and the current position. And then the direction from the previous to the current will be given as this, so we subtract the previous position from the current position. And then the inside direction, we use this inside turn dictionary on the particular direction where we're currently walking in, and this will give us the inside direction. And then we just append 2 new positions to this list, and one of them will be the current position plus the value of the inside direction, and the other will be the previous position plus the value of the inside direction. And then we return this list, and then finally we can use, in our solution, we use this list of positions just one step inside to find all the positions inside. So how can we do that? That will be done by this function, or at least I will count all the positions inside. So we'll have a queue around which enqueues all the positions that might be inside but we haven't considered yet. And then we also will have a set of visited positions around. So that will eventually contain all the positions we visited, but at the start we'll initialize it to all the loop positions. So essentially, if we are inside, we don't want to go across the loop because that will put us to a position that is outside. So that we don't want to consider any position that's part of the loop anymore. And then what we can do is we start with the count of 0, and then while there's something in the queue, we get the current position from the queue. And then if the current position is already visited or part of the loop, we are not interested, we continue. Otherwise, it's a valid position inside, so we will add it to the set of visited position. We increase the count of inside positions, and then all the neighbors of this position are potential candidates for the future. So we go through all the neighbors and append them to the queue. And yes, that will give us the inside count after we go through all the positions in the queue. So let's go through the solution again. So what we did was, of course, we passed the lines, place the correct pipe at the starting position. Then we use this get loop positions function to get us a list of positions which correspond to the loop. Then we figure out whether this list of position goes around the loop clockwise or anti-clockwise by counting the number of right and number of left turns. And the number of left turns we figure out by just reversing the list and counting the right turns again. Just a little trick. Once we know whether we go around clockwise or anti-clockwise, that will tell us how we turn, which way turn you turn inside. So if we go clockwise, the inside will always be right turn. If we go anti-clockwise, the inside will always be a left turn. Then with that, we can figure out all the positions one step inside. And once we have those, we can use that to find all the other positions inside and count all the other positions inside. All right, and we're given 4 test inputs this time. We, of course, run our solution on all 4 test inputs. That looks good. So we'll also run it on the real input, and it turns out that also gives us the right solution. All right, I hope you enjoyed day 10. Best of luck for the future, and I will see you around.